All right, well, thanks everyone. I have the unenviable task of trying to summarize and connect the dots between, I think, a rather vibrant discussion over the last 2 days. So what I'd like to do is really pose a challenge by recapping through the eyes of a Martian. So we'll try to ask that question. My blood does flow Martian red, and I can't, unabashedly, I will say that. So I'm going to try to look from what we've been discussing through the eyes of what Mars needs and what we're trying to do with Mars. Let me go to the next slide if I can figure this thing out. Hopefully that. So let me start with a challenge that John Grunsfeld and I have talked about for a long time. And really it gets at why do we even bother? Why do we have a space station, although all the benefits? And really it asks the question of what is our fate? And we've learned from going into space that cosmic collisions are the rule of thumb. They have, in fact, in the words of Stephen Jay Gould, they are the reason we're here. If you played the tape backwards, God knows it might be giant colonial microorganisms building pyramids instead of, hominids. But the real question is, we're here because of a law that Alfred Russel Wallace suggested about islands about 150 years ago, that single island species don't survive and maybe single planetary species don't. When John first said that, it struck me as a parallel for why we have a space station and why we have visions of places like Mars for all those reasons. So I would posit with you that maybe it is the International Space Station in Mars, connected intellectually, that is one of the reasons why we may survive. So the premise of this conference has been really, how could we use an object in low Earth orbit, a national and natural laboratory in many ways, to help us learn how to explore Mars ultimately with us. Now, there was a question asked yesterday about, when will we get to Mars? And I would sort of say, A, we're already there, and B, August 2012. August 2012, folks, we will put a national laboratory in the service of Mars. And it's taken us a long time to think about that, but I'll try to explain how that works. So let's start with a tale of two planets, not Dickensian really, and ask, what can the space station really help inform us about this world? It's taken us a long time to think about that, but I'll try to explain how that works. So let's start with a tale of two planets, not Dickensian really, and ask, what can the space station really help inform us about this world? And there's one critical factor, and I think it's really important. Where is the space station located? Well, this is all about the partnership that I would like to underlie my talk. Science is a connection that Dr. Scott Pace made a good point about a few moments ago. It can provide the level 0 requirement for the why, which may influence the policy and several other things. So we have a good record in science for the last 51 years at NASA and internationally. That record of understanding environments, learning about climates, exploring new worlds, asking, are we alone, where are we going, I think is written in the myriads of papers we all read. And in fact, Mars is a good example of a place where the benefits of the legacy in Earth science that I think all of the collective nations interested in the International Space Station are working toward, as well as those from Mars science, which is an Earth-like planet, come together. So in fact, it's a natural thought that what we could do with a space station in advancing understanding Earth and what we would want to do at Mars could inform how we explore Mars. So I think that partnership in science will produce a partnership ultimately in policy. Now, whether the humans can get there sooner or later in that partnership is a question we can debate for a long time. So let me quickly start then with what really it is we collectively as nations and within NASA are trying to do with Mars. Because we've come through various cycles of understanding, and we're still in kindergarten. We know, can't add up the Martian rocks well, or whatever bioscience we choose to say. But we really have a program strategy that we put in place now 11 years ago, it seems like yesterday. And that strategy was understand environments and histories of another world to ask the tough question, really, are we alone? And that question has plagued us with Mars, because we've just learned about how little we're alone here on Earth. I think the comments yesterday about the reactive functional microbial surfaces is an awareness that we all need to bear mind to. But this is a tough question, because we went to Mars with flagship on the coattails of Apollo with Viking. Many of us were interns with that program, some of you probably as well. We went there with eyes wired shut in the 70s, and we found a planet that didn't work the way we expected. I mean, it was a fantastic mission. Viking was an unqualified success, but we didn't see the signatures we expected because we took a terracentric, simplistic view of that world. And that was the right way to go. I mean, who can go back and say? But the Mars we attack now is a more systematic, stepping stone scientific logic path. We're not leaping into life detection because we don't even know what environments it might have been preserved in. We'd be like asking yourself to go to your backyard and find me a fossil that explains the history of life on Earth. Are any of you from the Ediacara Formation in Australia? I don't know. It's a great place to visit, by the way. Or the Burgess Shale in Canada, or any of these other places where early life. We're not. We don't find those things. We didn't even recognize nanofossils before some awareness from space. So the questions about Mars connect stuff we know is important for climate and life, liquid water being that magic universal solvent, how a planet's climate can change. This is relevant to Earth. Our planet has changed in environments. We know that from the rock record. And then how would we see habitats that are extant today, given what we think we understand about self-replicating chemistry that we call biology, and the past ones, preservation. We don't find dinosaur bones sitting here in DC at the same scale we find in the Mars formation of Colorado, for example, for a good reason. And so we study Mars that way, and ultimately, so those women and men could maybe be the great Eureka finders. So this is a sort of a strategy driven by science. It's led to good policies, partnerships now across multi-nations. And ultimately, that strategy will converge on the fact that we'd like to go there. And you might say, well, gee, we can do it with the robots, and we can. And some of us had conversations for the last 10 years of, well, if you were on Mars for a day, equipped as John was capably fixing Hubble, how much work could you do if the safety rules weren't quite, programmed by the minute? That might be a little tough. I know our MOD guys would like to do that, but let's just say they are 8 to 20 light minutes away. They might get a license to do things a little differently. But what could those women and men do equipped for a one-day EVA? And really, when we do the math, and it's inescapable, they could probably achieve what we've achieved with one of the Mars rovers in 2,600 days in a day or two. Now, we have human flight systems and all the capabilities that those bring. We would accelerate the pace of learning. We don't always have to go fast. I mean, giant Galapagos tortoises live to be 250 for reasons of pace, but it's often helpful. So this is our goal, and I think whether it's the next big step after station or not, it's a question we need to keep asking. But let's go back to history for a minute. The 1950s begat the space age and the information age, of course. And our vision of that, from Collier's and other magazines, was stuff that we didn't do. It seems that's, so today we think out 20 years, and we plan things that we might not do. Now, we did do station, and that's a great hallmark, I think, of all of us in this room and the people interested. So there's the vision, and the reality was, for Mars, that. Who would have thought, standing on the shoulders of Apollo in '72, that we would have sent dozens of robotic things that could do things we do in labs? I mean, I'm reminded that the labs on Earth were barely able to study the moon rocks when they were first brought back in '69. We weren't ready to make the measurements that showed us how rich the history of the moon was. We learned what we needed, and hence we applied them. The feedback has been incredible. But this is the Mars we have. Most of these are the missions that are planned. They're in the architectures in NASA and ESA, in Japan and Canada, Russia too, and they show even some possibilities that we might still get to do. But this is an incredibly rich learning experience with robotics that I don't think we predicted. I'd like to show this picture, because the picture at the top shows Gene Cernan in Taurus Littrow in '17, where we left the shores of deep space the last time on the moon. The picture below shows the view from Opportunity. It hit the hole-in-one, it's master's time, so we can say that, on Mars in January of 2004. And below is truly in various Mars analogs. Because what we've realized, and this is where station's important, that we don't know our neighboring worlds very well. We come terracentrically, and we learn to apply the reasoning that explained Earth to Mars. And so scientists, like many of my colleagues in the geosciences, apply what explains ancient environments on Earth to Mars, hoping to find the physical-chemical connections. And we can use station as a way of exploring how well we would do that, both being there ourselves and not being there ourselves. So I show you my search for Mars on Earth there as a legacy. So let me take a minute and remind you about the Mars we now see and about the revolution that we're still in. It's hard to be in the middle of a scientific revolution and try to figure out what's really going on. And that may apply in many science fields, so I understand we don't know about the missing mass of the universe, and these are big questions. But the Mars we see now is one that is phenomenally inexplicable in the sense that a small planet with a smaller heat engine than Earth has ripped itself apart at scales of continents against all odds. This is just a graphical view of one of the definitive data sets from our last 10 years of remote sensing, the topography of the Great Valles Marineris. How do you rip a planet at the scale of Canada or the United States apart with a thick crust that shouldn't deform that way? Real paradigm challenge. How do you explain the emission of what we think were Newtonian fluids, hint, probably liquid water, saline water, from hillsides ubiquitously around Mars in certain environments? And really, this was so scary that the creator of this first result told me 6 months before he dared publish, I don't want to show anyone but you this, Jim, because they'll go crazy. I'm not sure what they'll think of it, So they waited 6 months to publish in Science, and Mike Malin's Gully paper suggested a few hundred. Today the counts are in tens of thousands. Wherever we look, we find hillsides that probably erupted fluids. And on Earth, of course, yours truly and many of our colleagues have been in search of the environments that are most like those on our planet. We learned, and in fact, we thought of them simplistically on our world, but when you apply that to Mars, you gain insight. So Earth, ISS, applied to Mars. And likewise, little did we know as we looked at Mars that we discovered ancient records of the action of fluids on this other world that mimic those ancient records on Earth that we take for granted. Okay, there were river deltas there, great, Mesopotamia was great, hallelujah. We see the rocks, okay, so what? Well, on Mars we found those. This is on the left, on your right, sorry, is the smoking gun for standing bodies of water that had to exist on the surface of the planet. This was so heretical when we tried to have a press conference in 03 or 04 about it. Several colleagues in our science organization asked, said, well, it's not important enough. But there it is, folks. Any geomorphologist who does this at all would say, no other way to do that. And this is one of the candidate landing regions, a fossil delta where water sat around for a long time. They're important on Earth, of course, as fertile crescents and any other things. So we've learned that to understand Mars, we need to find Mars on Earth through physics and chemistry, not just, the great pictures I'm showing you, and understand what that can tell us about how to explore that world. Well, the minute we look at Earth analogs, we think of space, Earth analog connections. John hinted at this yesterday. It brings to mind the connection between space station and environments. And yes, the environments on Mars seem so, non-terrestrial, but they are linked in physics and chemistry. And then we come to how we've been exploring Mars for the last 6 years. Here's, if you look carefully, you see a little artist rendering of Opportunity on its crusade across the planet, now, nearing another crater on the planet that will show how intrepid it's been. Just remember, folks, we designed these giant Galapagos tortoise moving vehicles to last for 90 days. That was the baseline mission. Initially, we actually thought 45 would be good enough. And today, when you're counting days in the thousands, you start to recognize the value of robotics in a partnership with people. Because these robots are an extension of ourselves on Mars. They're not autonomous. We do tell them what to do, and they listen gainfully. Better than most, probably, crew members and teenagers, but I'm not sure. So this kind of place raises a question. The flight rules for Apollo would not have allowed any of you that are astronauts, John, or anyone, to go into that type of environment. But we could risk a rover after a long voyage. And the results from these rovers, from these little robot, if you will, extensions of ourselves, have been phenomenal. Here's a result, seemingly a boring little piece of geologic history, that attests to the fact that Mars may have had environments that preserve carbon-bearing stuff. And this is from the Spirit rover, now sitting mired near home plate on Mars. But the result, the preservation potential of carbon on Mars, 5 years ago would have been thought heretical. We can't find the carbonates. It's missing. What happened to it? Well, it was fractionated and we lost. We had theories, and now we found it by being there with a small, a small robot the cost of half of a Cameron movie. So I think we have to bear witness to what Mars is now showing us as we think about the challenge of station to wherever to Mars. We now see exposures of ancient bedrock peeking out through the dunes of the planet from our reconnaissance. But this reconnaissance you see from the Mars Reconnaissance Orbiter was actually heretical when we first suggested we need this kind of mission. Several colleagues, very capable ones, policymakers, said, well, you've done enough orbiters, you're done with it, let's move on. We said, no, we're not done. We can't go everywhere, and we have to know where to go. If A, we're going to send people, if B, we're going to bring back samples. So let's go another step. So now we can see things at new scales, they're more personal. We can see records of things that even offer us hope that there may be environments on Mars that are accessible to robots and maybe even relevant to human exploration. I'm not saying we should send our crews down the first lobster we find, but we found them on Mars and on the Moon. And these offer refugia and possibilities for life. We've also seen that Mars is even more dynamic than we ever thought. And this is why applying space station and the learning at Earth is so important. Little did we know that Mars is a planet with not only dynamic atmospheric exchange. Every year it exchanges 25% of its atmospheric mass with the surface and back up again. If you think about that on Earth, it's scary. But this little neighboring planet does that. So for Mars we have dynamics of avalanches. We've seen the record of cosmic collisions in just the lifetime we've had robots on Mars. Cosmic collisions happen at different scales at different times. These are just some of them. We've also seen on Mars eruptions of gases under pressure producing these strange wispies, or whatever they're being called now, probably emissions of gas, of carbon dioxide sublimating dynamically, producing geysers. These are all things we have to get to know before we inject ourselves, or even our more prized robots, into this world. So there's work to be done.
Is mopping the horse, which 10 years ago we thought were made of solid CO2.
10 years ago. Solid CO2, that's what physics says. Well, no, that's not what physics said, but that was an inference. So we have to be careful of applying first-order things to another world where we have very limited observations. The space station will help us look at Earth systems with observation that can be verified on the ground, the way we do all our science on our planet. So when we look at Mars now, we can see the record of change in the polar caps. The left is just the topography of the great ice rink at the north, and the view at the east shows the record of paleo drainages made in that, suggesting multiple chasmata with sizes equivalent to pieces of the Grand Canyon in this great ice sheet on Mars. So now we suspect that there's a much richer ice record of change in climate on Mars that reflects when Mars was wetter and warmer. The Phoenix mission, a discovery mission, again, a robot designed for a seasonal measurement cycle on Mars, guided by robots, is a good example of what you can do more autonomously. But again, the human control allowed Phoenix to not only see and verify the existence of water ice in the shallow Martian subsurface, but it also identified chemistry, not contaminant chemistry, that has a bearing on the stability of water. Perchlorates were suspected, now we've discovered them pretty definitively with a wet chemistry experiment. So why do I show you all this? I show it to you because the Mars we're starting to see is an ever-changing landscape. It's a science question. Ultimately, we have to ask ourselves, is that question space, as we get better at it, which we will, is that question space openable to human explorers? I would maintain yes. I think we're pretty good at things, but let's move on. Of course, we've seen the ice exposed by new impacts, so if you didn't think it was there, well, Mother Nature has exposed it for us, again, definitively, and there are more and more of these things being discovered just because we have the assets there. Same thing is true of Space Station. The International Space Station is the lab that is the asset somewhere relevant to making discoveries. And finally, just the record, the rogues gallery of some of the fresh impacts. Just remember, folks, 10 years ago, 12 years ago, I guess it might dates me, Mars was an ancient geological world where all the action was 3.7 billion years ago, and pretty much since then it's been a dead world, frozen in time, that's it. Well, not so. It's being rocked. We've wandered up randomly across the plains of Mars on multiple meteorites. What's the probability of that as you wander your backyard running into a bunch? Most of us can calculate that and say it's not too likely, and the eBay guy selling them will admit that. So I offer to you a bridge question. We have our International Space Station, this national lab, and we have a lab we'll be sending to Mars launching this Thanksgiving time. Dave yesterday said, right after Thanksgiving, if you're watching football or basketball, or in my case, hockey, you can think about this vehicle. This is Hubble Does Mars. I know that's heretical for all of you astrophysicists, but we're going into a new domain, and we will be operating it with the time delay and all the required latencies by the speed of light. But the MSL is as big as something to carry you or me, equipped with lab gear that is better than that we had to look at moon rocks in the late 60s. Better. On the surface of Mars in a robot. It's an international mission, and I think it will be a learning ground, a lessons learning ground for how we will need to intelligently explore with human beings. And it will also guide us into the questions we can use space station for to train ourselves, because the training in those ops, for whatever scale human mission we can do, ideally longer with more driving, but whatever. So MSL, of course, is a lot bigger than the other robots that we've sent. Notice Sojourner there, the microwave oven for scale. MSL is big enough to take me and drive me across this room, scary as that is. What makes MSL interesting is it is the outgrowth of planning from science. And Scott said that. This is the policies that led to MSL, the Curiosity rover, were driven by science goals, asking not, is Mars alive? And that's the underlying big question. But how would you even tell? At the level of the rocks and the gases and the ices, how would you tell? In a place that's not a parking lot, we've landed in the parking lots and they're all fun, we're going to go to the interesting terrain. So MSL is designed to go beyond the simple science catchphrase of follow the water, always good to do even here on Earth, to really look for signs of what's happening to the carbon. And that presumes that the carbon is important in biogenics and and how biology works, fractionating it here on Earth, but that's the premise. It may not be the right premise, but it's equipped to answer questions different than that. So we're going to do the geology, because Mars is a geological world, but we're going to assess what we call biological potential. Could it have been habitable in the past? It's really all about a stepping stone, if you will, an incremental approach to being ready to ask, can we send people? And what really will inform us about the biological prospects on Mars? And when we first designed MSL, the thought was, well, maybe we need 10 of them. And then it was, maybe we need 2. Now we've got 1. This is our mini space station on the surface of Mars. This is the kind of landing site that's being considered. Ed Weiler will select the final one in the early fall before we launch. But if you see the rich stack of rocks colored there because discriminating chemistry, this is the kind of thing you'd see driving along a road cut in Colorado, or in the Caucasus, or in cuts through the Alps. Cross-sections of stratigraphy, which is history, which is different chemistry over time. This is the way we get to know how a planet plays up together. And so we're going to be going to a place like that. This is, by the way, this is game-changing, folks. The landing site will dictate the science you can do. Just for scale, one of our commanders there for scale from the Navy, sir, next to MSL. So this rover, by the way, just for scale, and again, these are the kind of scale comparisons we need to consider with space station, has gone from carrying 5 kilos of actual instruments to more than 100. So we went from the Mars exploration rovers, a few kilos of good stuff supported on a mast and a little arm, to something where the mass of instruments is something like 20 times that. So we've really extended ourselves. Now, why did I show you all that? Well, MSL will train us into how we need to think about the concepts of operations of exploring Mars. It will also inform us what could we do here on Earth to get ready. And we have desert rats, and we have Houghton, and we have, I think, the Antarctic, where our National Science Foundation here in the US is ready to work with us in a partnership to do the kind of things we need. And then the next step after that, for all of us, written in the Decadal Survey of Planetary, is to bring the stuff back. And this is, kind of mini Apollo without the astronauts robotically, as we call it. And this kind of mission will involve partnerships driven by science and policy. Already that partnership is established, with our colleagues in Europe. Certainly we need the colleagues in Canada and Russia and Japan and other worlds to do it. But it'll be, I think, a poster child for how we ultimately get to do whatever kind of human mission we choose to do at Mars. MSR, Mars Sample Return, by robots, will return stuff to labs. Now the labs we have here on Earth are well equipped to do things that I consider nearly impossible. Parts per trillion measurements of stuff that can tell you how old things are, where they came from, whether they're biologically processed, contaminants, we can find the hexavalent chromium, if you're worried about that. We can do all that. That was supposed to be a joke, folks, but I guess you didn't get it. Okay, well, just a nasty stuff. So, the question I raise, one of the questions I leave you with in my remaining time is, so we have these labs on Earth at Johnson Space Center and universities, Goddard, wherever we want in Europe, ready to process samples of stuff from Stardust, from Mars, from the Moon, from Apollo. What would it take for us to imagine inverting that and actually putting a mini laboratory on the International Space Station that could actually look at stuff? Not only space dust that we could collect, but also materials. To think about it as a way station for sample analysis in low Earth orbit. Not to say we need to put the samples there after they're returned from Mars, but as a thought, that kind of question is one I think we need to be asking. What really can we do with station to prepare the way for Mars? So I guess you can't read the bottom because it's cut off by the table. But I posit, what is the best we can do beyond the already existing scope of the International Space Station to use it as a true preparation step for humans to Mars? What is it? Is it just learning all the things we talked about yesterday, adaptation to microgravity for long trips, countermeasures, rehearsal? Well, I'm going to suggest a few things. The first thing I'm going to say is the space station is the best place I can imagine to test out the new kind of remote sensing stuff that I think we'll need to prepare the way for humans on Mars. We've done great for the robots, and they're willing to land at 50 Gs. Most people would prefer not to. I think we had a few that landed slightly hotter, and Don Pettit can tell you his experience. I'm sure it was gainfully interesting. But the station offers power, data, services, command and control, smart people in multiple control loops to start going beyond what we can cram into small free-flying spacecraft for one of a kinds to go to these worlds, whether it be low Earth orbit or other worlds. Imagine the kind of assets that we never have. I would love to have a robotic planetary mission to Mars with 4 kilowatts of power for an instrument. Well, my own spacecraft might have 350 watts continuous for a typical Mars orbiter. So just think of the power of that. Also, the idea of having an environment where we can plug and play and watch technology evolve as we get better is important. So I've shown down there just cartoons of the kinds of things you could imagine doing, of the myriads of them, in a testbed pathfinding environment on station. Many of us use the world's most capable orbiting vehicle. So the station allows us to extend that. And so as a laboratory for investigating instrumentation that might be used as a reconnaissance step before we send the women and men to Mars, the station is about the best thing we got. And to use it for that, I think will bridge the gap to Mars. Next, of course, there is learning to play, as Seppi said yesterday, with the human-robotic partnership. To date, our human-robotic partnerships are measured in we control the Canadarm from in the station, from in the shuttle, of course, and it's an extension of ourselves locally. And the partnership is sort of, we're in control authority and it does some things. Extending that partnership is really important. Dexter is a good example, the Canadian robot, but there's other examples too. What if, I just did the wrong thing, shucks. I want to go back, there you go. What if we could actually operate robotic assets for science, measured in the concepts of operation, from station in places, to simulate what we might have to do in support of human missions to the surface of Mars, or even preparatory human missions. What if we could actually teleoperate in a supervised fashion things that go to places where we won't send people, inside the active lava crater of Mount Erebus, or Makawao, or the volcanoes of Iceland, whatever you like. What if we could do that? That would extend our ability to understand those relationships and really evaluate what we'll need to know from Mars. And of course, there's also extending things in the area of the technologies that are already in our RCT programs, the kind of thing Franklin Chang Diaz has done with really high power electric propulsion with VASIMR and other variants. Mini magnetospheric plasma propulsion is another one we could experiment with. But the station offers us possibilities if we align them for going to Mars. So in my last couple minutes, I'll leave you with a couple of thoughts. The first thought is, Mars is a natural laboratory actually for understanding Earth. Formed in the same neck of the woods, we think we understand that much about planetary formation, to inform us about what happens to worlds when they grow up differently, climatologically, even in terms of habitability with organisms. It's hard to imagine the Mars now as being totally absent of any biology. And maybe the biology there now is that which we left there ourselves from the landings of the Soviet craft and the Vikings and the other things. But nonetheless, it would be hard to imagine it's so devoid. But again, that's a biological question. So it's a natural laboratory for us to explore Earth, but so is the International Space Station, for all the reasons that we've summarized here today. So I leave you with a little equation. It's not F equals ma, and I know the M is important, John, but it's ISS plus the robotic exploration we have planned together, at least the NASA ESA parts and with other partners from Canada, is the ingredients to inform humans to Mars. And I'd like to just remind you of this chart that Brett showed a year ago, which shows the sort of evolution of what was an evolutionary strategy, naturally through the moon, a very good place for learning, as we've all said. But the things on the left are really where some of the energy on station already exists. I put ones in blue that we could extend its use toward the Mars question. I think the community would be really excited to do that across multiple agencies and international partners. And really, that partnership with the Mars Robotic Program internationally is an important one. How do we learn from what MSL can do, Curiosity, MSR could do, and apply it to what the International Space Station can do? I think there's answers. It's not for me to give them, it's for me to suggest some things we could do. So I think I'll finish with two thoughts. Number one, this is what you'd see of Earth if you were on Mars. So the tie is severed, folks. We can learn here with Houston in command or close by, but when we're on Mars, we're on our own. You know, speed of light notwithstanding. So we're going to have to learn a lot. And the station is the place to train ourselves in that, in natural ways. And it's close enough that we can make mistakes and recover. It really is. We recovered very fortunately on Apollo 13 on the moon, but the station is much more forgiving. And then I'll finish with a chart that Ed Weiler and I showed Sean O'Keefe when the vision was being codified. John will remember it, which is science does matter. It may not be the ingredient of the ultimate why, but as Scott said, it does help shape the level 0 policy things that we agree we're going for at least part of this reason. So if scientific interest, understanding, and impact on us as living things on planet Earth matters, there is a kind of a progression. I'm not saying it's linear. It's probably a hyperlog plot, but there is a progression. And as we understand what we can read in our own history, we need to go beyond. To the moon? Yes. The samples have shown us that already. Even the old ice that we know now exists on the moon could do that. The telescopes can show us about the exoplanets that look more and more like Earth-like worlds or Venus-like worlds or even Mars-like worlds. But ultimately, Mars is the nearest place where we can ask, credibly, well, were we at least alone in terms of the kind of biology that we think about? And I point this out that we had proposals at NASA in my time at headquarters that suggested that 16S gene expression experiments on Martian materials would be actually worthwhile to sense where that life actually came from. Of course, Chris McKay has often said, maybe we are actually the Martians, we're just here. That would be interesting. But the space station is part of the equation of making that Mars come alive, because no matter what we can do with robotics, how far we can go with the investment we've had internationally, it won't be enough. So the ultimate question is, are we actually wanted there? And I don't know, but I do think, as I finish, that we are wanted here. In the words of the spacefarers that have gone, the space station is where we are today. The robots are on Mars, and so our challenge is to connect those dots through whatever pathways make sense. I think there's multiple pathways that would use the space station toward a Mars goal, which, by the way, it's interesting to note that 3 presidents in the United States have all supported that in speeches, actually 4 if you go back to Bush 1. So there does seem to be a common theme here. It's not a bad thing to have an aspiration to do that. So I guess I'll finish with the thought that sending humans to Mars will be beyond any decision made in the history of exploration by humans. Be beyond the Columbus decision to come for a new world, or the Magellan decision to circumnavigate, or the Drake decision to circumnavigate. It'll be beyond any of those, or any others we imagine. And so it will take a collective, the collective intellect and policy and governance to do it. But I think it will be worth it. And if we commit to it now, it'll be like building the cathedral. We'll do it. And we'll have the legacy behind. So I'm excited the space station is part of that equation because I think it's a critical element. And thank you for your time.
enemy of good, or so my wise grandmother taught me. Over the last 2 days, a lot of attention has been given to mitigating risks. However, life cannot be lived risk-free, and space most certainly cannot be explored risk-free. And trying to take away almost all risks will only succeed in keeping us earthbound. So I believe we should take my grandmother's advice and opt for good enough for the human exploration of space and of Mars. This means that we should not wait for us to invent a way to have almost no radiation exposure for astronauts traveling to and from Mars. As we worry about the impact of radiation, instead of forbidding the astronauts to travel, I say we should do 3 things. 1, we offer the women and the men going to Mars lifelong health care in case they do get sick after their trip to Mars. 2, we inform these would-be Marsanauts completely so that they can sign a waiver acknowledging that the risk is taken by them knowingly. 3, we need to let go of the idea of a risk-free human to Mars mission and, in that sense, lift the ban on the limit of rats for Marsanauts. Accepting good enough technology and risks for a human to Mars mission steers us to the safety of a global Mars mission. And listening the last 2 days of discussions and presentations, that's how we all agree that we want to go globally, to go together. We're about to send Curiosity to Mars. Let us all pledge to take the next step and send her sister, Ingenuity, and that's us, the humans, to Mars no later than January 2029. Well, let's contemplate that thought and perhaps have another discussion about this in a year or so in another conference. But contemplating that usually goes better over drinks, so I invite you upstairs to have a drink with me and discuss this. Thank you all for coming. It was a great conference with your help.